Hi everybody, it's Scott here. This is the first video in a series looking at different joining methods in engineering applications, and in this video we're going to take you through a bit of an introduction and an overview of the different joining methods that we have available to us as engineers, and we're going to explain the different examples of welding that we have access to typically in industry. Let's start by taking a look at the overall chart that we have that captures most of the manufacturing methods in the different categories. So we have forming methods over here, the main one being sand casting. We have machining methods, including turning, drilling, and milling. And in this series of videos, we're going to take a look at the joining methods, which might include things like welding, screws, rivets, splines, and keys. These ones down here. I've got a little bit of a different way of looking at this, so I'll go to this next slide. And so this is a way of categorizing the different joining methods available to us. We can split them all up between permanent methods or relatively permanent methods. A lot of these can be undone with a bit of work, but not very easily. And then we have the temporary methods on this side of this Boolean tree. Underneath the permanent methods, I've divided them into two separate categories, those that are joined using liquids. So this might include welding, brazing, soldering, and also the use of adhesives. And then on the other arm of this category, we have plastic joining methods. So I'm not talking about plastics. What we're talking about here is plastic deformation of our materials to enable them to act as joiners. So things like riveting, staking, forming, and swaging are all ways of joining two components or two materials together by plastically deforming those materials. If we look over at the temporary side of the tree, we've split them up into threaded and non-threaded fasteners. So under the threaded fasteners, we have common things like bolts and screws and studs and nuts. And then in the non-threaded category, we have options such as pins and keys, splines, clips, and interference fits. So this is the way we've chosen to categorize the different methods, and we're going to work through them in this basic order now. So we're going to start off by looking at a variety of different welding processes that we have available. In general terms, to create a weld, the interface between two solid materials is melted. These liquids from these two materials are mixed together and then they're allowed to solidify. Sometimes we can also use a third material, such as a melted rod or a wire, that we can add to this weld pool to actually increase the amount of material there and to help form a stronger joint. This is an optional thing that we can do. So what do we have to think about when we're creating our welds? Well, first of all, the materials have to have approximately the same melting points. So for instance, we couldn't try and weld lead to steel because lead will melt at a much lower temperature and the steel won't even be getting soft yet. And so the lead will all run away before the steel has got to the point where it will melt. So we couldn't do that. The materials must be able to mix, so you might have an example where you're trying to weld lead to plastic. If you look up the melting points, you might find they're very similar, but because these materials are so dissimilar, they won't want to mix together happily, and so we're not going to be able to create a workable weld between these two materials. The material properties near the welded zones may be affected by the heat which we've added to create the weld. This is something that we have to keep in mind when we're welding things. For instance, if you have some hardened steel that you're welding, that hardened steel may have been hardened via a process of heat treatment, and by welding it in the region around the weld, the different cooling rates when it's being welded and solidifying may actually change the material properties. So it could potentially become softer. It could also become harder in that heat affected zone and actually become more brittle. So this is something that we have to be aware of and do some research on the materials that we're welding together to ensure that we're not altering those properties in a way that might be detrimental to the final component that we're building. Another thing that you should keep in mind is that any coatings, such as galvanizing that we might have on steel to stop it rusting, these coatings must be removed before we can weld them in order to create an effective join. So if we were to try and weld with the galvanizing on the steel, then that gets into the weld and causes impurities, which we don't want. It can weaken our weld. We should also be aware that some metals like aluminium, they have a strong oxide film on them pretty much all the time. And in order to weld the metal underneath, we need to get through that oxide film. And so we have special techniques and special welding technologies to be able to do that. We should also be aware that the chemical composition of this weld pool, the melted metals, may be affected by exposure to the atmosphere. So if we have some steels and it may have a certain amount of carbon in it, if we melt this, the carbon may come out of the steel and form CO2, and so we'll have less carbon in that area of the weld than we otherwise do, and that could change the material properties in the weld. These are all things that we need to think about and keep in mind when we're designing our welds. Let's take a look at a few different practical examples of how we weld metals together. The first one we're going to consider is oxy-welding, also called oxyacetylene welding sometimes, or oxypropane welding. And what we do to create welds using this technique is to generate heat by burning oxygen with a combustible gas such as acetylene. You can see the guy on the left in this picture. He's got his glasses on there, so his eyes aren't exposed to this bright light of the gases burning, and he's using this torch which mixes the gases together with oxygen, and there's a flame at the bottom which has a nice tight shape to it so you can direct the heat accurately, and he's melting metal, and in his left hand here he has a filler rod which is allowing him to add extra material to the weld as he goes. So we can use this technique. It's quite fine, and it can be used to weld thin to thick pieces because we can direct the heat where we want it to go and put more heat into the thicker piece and prevent the thinner pieces from melting away. That's one of the advantages of this technique. It's also something that we can do underwater. So if you get this combustion going, you can actually do it with surrounded by water, and even though you're losing a lot of heat to the water, if you stick at it, you can actually get the required amount of heat into the metal and actually weld underwater. And this guy is a very specialized technician and gets paid a lot of money to do that on offshore oil rigs and the like. We can also adjust the balance of oxygen and acetylene in our mix to allow us to either add or remove carbon from the different steels that we're welding. So this is a further option we have with this technique, which is useful to ensure we get the final material properties in our weld that we desire. Another common welding technique is called arc welding. And in this process, we use heat, which is generated by an electrical arc between an electrode, which is part of the welder, and these materials that we're welding together to melt the material. So in this image on the right-hand side here, we have a typical small hobbyist size arc welder, and we would put an electrode into this side of the handle, and this is our earth lead, which we connect to the part that we're welding to complete the circuit. And then when we turn it on and we strike the arc, we create an arc here, and that progressively melts our electrode, and that electrode contributes material like a filler rod to the weld as we go along while sustaining that arc. On the outside of our electrode we have commonly a coating, and this coating melts due to the heat, and it forms a slag layer which helps both prepare the metal surface and also protect the weld metal when it's still molten from the atmosphere, so we can keep out some of the impurities and the loss of the carbon that we might otherwise see from exposure to that atmosphere. Unfortunately, we don't have as great a control over where we direct the heat using this process, and so we can't as easily weld thin to thick pieces, so there's a limit to the difference in the sizes of parts that we can weld together, and typically we use this technique for quite heavy industrial parts like 5 or 10 millimeters thick or bigger. As I mentioned, that electrode coating on the outside helps prepare that surface of the weld and also protect it against exposure to the atmosphere while it's cooling. Once the weld has fully cooled, if we want to expose this weld and perhaps do another pass of weld, then we actually have to chip off this slag layer once it solidifies with a hammer and make sure we've removed all of that before we do the next pass on our weld if we need to build up a lot of thickness. We can also use a similar process, but rather than having a slag layer that protects the weld, we can shield our weld pool by pumping in an inert gas and making sure that's enveloping the weld as we're welding. Typical names for these techniques are either MIG or TIG. This is a MIG welder that you see here. A MIG welder is differentiated by the fact that it has a roll of very thin wire here, which is fed all the way through to the gun here, and so that is like a continuous arc welding technique, and the wire actually moves quite fast and sustains the arc and is consumed at the same time. And then we shield that by hooking this up to a gas bottle, and then we pump gas through this as well, and so that gas surrounds the weld when it's very hot and prevents that oxygen getting in there. TIG is another option, but in TIG we don't have the reel of wire that's constantly fed out to the gun. We have a tungsten electrode which is used to sustain the arc, and that's not consumed, and then we periodically dab in, if we need it, some filler rod as we go, and then we have the argon gas shielding this whole process as well. It's also quite common in industry to see robots performing these welding techniques in modern mass production. So that's MIG and TIG welding, which are variants of arc welding. The third common welding technique is called electrical resistance welding. So in this example, we take typically pieces of steel. So we have two pieces of steel in the center here, and then we have an electrode on either side, which we clamp up with a lot of force to ensure that this is all compressed together and we have a good contact going through all of these bits of material. And then we run a high electrical current through this assembly basically, and given that these electrodes are made from copper and they have a lower resistance than the steel, the large electrical resistance occurs through the steel, and that generates a lot of heat, which then melts these two steel plates together. This is commonly called spot welding. So the heat in this circumstance is generated by our I squared R electrical power relationship at this interface between the two materials. They then melt, and given the differences between steel and copper, the copper doesn't actually get stuck to the steel, and we can pull that away and it doesn't actually get welded together. We need to ensure that we've got high force here because these plates might not perfectly align, and we need to have a good electrical contact through here. So the machines that do these spot welds are quite big and robust, and they typically have a powered clamping mechanism to hold this together quite firmly. And it's used quite commonly in the automotive manufacturing industries, where they have people and even robots which can create these spot welds at very precise positions on the car in order to join all the different body panels and floor panels together in a highly efficient production process. There are a few other variants on this theme of spot welding, and one of them shown here is seam welding. So rather than two single electrodes being pressed together, we have two rollers and they roll continuously, and then if we feed in our sheets of material here with an overlap, then that will be continuously welded, seam welded together. And another variant of that again is slightly different, called mash welding, where we try to eliminate that overlap by squishing them very hard together with minimum overlap. Those are the three most common types of welding that you'll experience in industry, and hopefully this video has given you a little bit of an insight into the differences and the things that we need to consider when we're designing for these different welding processes. Thanks for watching.